A water clock or clepsydra, Greek kleptane, to steal, hydr, water, is any timepiece, in which time is measured by the regulated flow of liquid into inflow type, or out from outflow type, a vessel where the amount is then measured. Water clocks, along with sundials, are likely to be the oldest time-measuring instruments, with the only exceptions being the vertical gnomon and the day-counting tally stick. Where and when they were first invented is not known, and given their great antiquity it may never be. The bowl-shaped outflow is the simplest form of a water clock, and is known to have existed in Babylon and in Egypt around the 16th century BC. Other regions of the world, including India and China, also have early evidence of water clocks, but the earliest dates are less certain. Some authors, however, claim that water clocks appeared in China as early as 4000 BC. Some modern timepieces are called water clocks, but work differently from the ancient ones. Their timekeeping is governed by a pendulum, but they use water for other purposes, such as providing the power needed to drive the clock by using a water wheel, or something similar, or by having water in their displays. The Greeks and Romans advanced water clock design to include the inflow clepsydra with an early feedback system, gearing, and escapement mechanism, which were connected to fanciful automata and resulted in improved accuracy. Further advances were made in Byzantium, Syria, and Mesopotamia, where increasingly accurate water clocks incorporated complex segmental and epicyclic gearing. Water wheels and programmability, advances which eventually made their way to Europe. Independently, the Chinese developed their own advanced water clocks, incorporating gears, escapement mechanisms, and water wheels, passing their ideas on to Korea and Japan. Some water clock designs were developed independently, and some knowledge was transferred through the spread of trade. These early water clocks were calibrated with a sundial. While never reaching a level of accuracy comparable to today's standards of timekeeping, the water clock was the most accurate and commonly used timekeeping device for millennia until it was replaced by more accurate pendulum clocks in 17th century Europe. Ancient Persian clock. According to Callisthenes, the Persians were using water clocks in 328 BCE to ensure a just and exact distribution of water from qanats to their shareholders for agricultural irrigation. The use of water clocks in Iran, especially in Zibad, dates back to 500 BCE. Later they were also used to determine the exact holy days of pre-Islamic religions, such as the Nowruz, Chela, or Yald, the shortest, longest, and equal-length days and nights of the years. The water clocks used in Iran were one of the most practical ancient tools for timing the yearly calendar. The water clock, or finjan, was the most accurate and commonly used timekeeping device for calculating the amount, or the time, that a farmer must take water from a qanat, or well for irrigation, until it was replaced by more accurate current clocks. Persian water clocks were a practical and useful tool for the qanat shareholders to calculate the length of time they could divert water to their farm. The qanat was the only water source for agriculture and irrigation, so a just and fair water distribution was very important. Therefore a very fair and clever old person was elected to be the manager of the water clock, Mirab, and at least 2 full-time managers were needed to control and observe the number of finjans and announce the exact time during the days and nights. The finjan consisted of a large pot full of water, and a bowl with a small hole in the center. When the bowl became full of water, it would sink into the pot, and the manager would empty the bowl, and again put it on the top of the water in the pot. He would record the number of times the bowl sank by putting small stones into a jar. The place where the clock was situated, and its managers, were collectively known as Khan Finjan. Usually this would be the top floor of a public house, with west and east-facing windows, to show the time of sunset and sunrise. There was also another timekeeping tool named Asteriab or astrolabe, but it was mostly used for superstitious beliefs, and was not practical for use as a farmer's calendar. The Zibad-Gonabad water clock was in use until 1965 when it was substituted by modern clocks. Egypt. The oldest water clock of which there is physical evidence dates to c. 1417 to 1379 BCE, during the reign of Amenhotep III, where it was used in the temple of Amun-Re at Karnak. The oldest documentation of the water clock is the tomb inscription of the 16th century BCE Egyptian court official Amenemhet, which identifies him as its inventor. These simple water clocks, which were of the outflow type, were stone vessels with sloping sides that allowed water to drip at nearly constant rate from a small hole near the bottom. There were 12 separate columns with consistently spaced markings on the inside to measure the passage of hours as the water level reached them. The columns were for each of the 12 months, to allow for the variations of the seasonal hours. These clocks were used by priests to determine the time at night so that the temple rites and sacrifices could be performed at the correct hour. These clocks may have been used in daylight as well. In Babylon, water clocks were of the outflow type, and were cylindrical in shape. Use of the water clock as an aid to astronomical calculations dates back to the Old Babylonian period, c. 2000 BCE c. 1600 BCE. While there are no surviving water clocks from the Mesopotamian region, most evidence of their existence comes from writings on clay tablets. Two collections of tablets, for example, are the Enuma Anu Enlil, 1600-1200 BCE, and the Amu-Elipan, 7th century BC. In these tablets, water clocks are used in reference to payment of the night and day watches, guards. These clocks were unique, as they did not have an indicator such as hands, as are typically used today, or grooved notches, as were used in Egypt. Instead, these clocks measured time by the weight of water flowing from it. The volume was measured in capacity units called qa. The weight, mana, the Greek unit for about 1 pound, is the weight of water in a water clock. It is important to note that during Babylonian times, time was measured with temporal hours. So, as seasons changed, so did the length of a day. To define the length of a night watch, at the summer solstice, one had to pour 2 mana of water into a cylindrical clepsydra. Its emptying indicated the end of the watch. 1/6 of the mana had to be added each succeeding half month. At equinox, 3 mana had to be emptied in order to correspond to 1 watch, and 4 mana were emptied for each watch of the winter solstitial night. India and Kamaswara Rao suggests that pots excavated from Mohenjo-Daro might have been used as water clocks. They are tapered at the bottom, have a hole on the side, and are similar to the utensil used to perform abhishekam, pour holy water, on Shivalingam. And Narhariakar and Subhashkak suggest that the use of the water clock in ancient India is mentioned in the Atharva Veda, from the 2nd millennium BCE. Gati or Kapala, clepsydra, or water clock, is referred to in Jyotishavadanga, where the amount of water that measures in Attica, 24 minutes, is mentioned. A more developed form of the clepsydra is described in chapter XIII, 23, of the Suraya Siddhanta. At Nalanda, a Buddhist university, 4 hours a day and 4 hours at night were measured by a water clock, which consisted of a copper bowl holding 2 large floats, and a larger bowl filled with water. The bowl was filled with water from a small hole at its bottom. It sank when completely filled, and was marked by the beating of a drum at daytime. The amount of water added varied with the seasons, and this clock was operated by the students of the university. The description of a water clock in astrologer Varahimaros Bankasiddhanta 505 adds further detail to the account given in the Suraya Siddhanta. The description given by mathematician Brahmagupta in his work Brahmasfuta Siddhanta matches with that given in the Suraya Siddhanta. Astronomer Lalakara describes this instrument in detail. In practice, the dimensions were determined by experiment. China. The water-powered mechanism of Susong's astronomical clock tower, featuring a clepsydra tank, water wheel, escapement mechanism, and chain drive to power an armillary sphere, and 113 striking clock jacks, to sound the hours, and to display informative plaques. In China, as well as throughout Eastern Asia, water clocks were very important in the study of astronomy and astrology. The oldest reference dates the use of the water clock in China to the 6th century BCE. From about 200 BCE onwards, the outflow clepsydra was replaced almost everywhere in China by the inflow type, with an indicator rod borne on a float. Huan Tan, 40 BCE 30 CE, a secretary at the court in charge of clepsydrae, wrote that he had to compare clepsydrae with sundials because of how temperature and humidity affected their accuracy, demonstrating that the effects of evaporation, as well as of temperature on the speed at which water flows, were known at this time. In 976, Zhang Sixan addressed the problem of the water in clepsydrae freezing in cold weather by using liquid mercury instead. Again, instead of using water, the early Ming Dynasty engineers Anxi Yuan, c. 1360 to 1380, created a sand-driven wheel clock, improved upon by Zhu Shuxu, c. 1530 to 1558. The use of clepsydrae to drive mechanisms illustrating astronomical phenomena began with Zhang Heng, 78 to 139, and 117, who also employed a water wheel. Zhang Heng was the first in China to add an extra compensating tank between the reservoir and the inflow vessel, which solved the problem of the falling pressure head in the reservoir tank. Zhang's ingenuity led to the creation by Yixing, 683-727, and Liang Lingzan, in 725, of a clock driven by a water wheel link-work escapement mechanism. The same mechanism would be used by Su Song, 1020-1101, in 1088, to power his astronomical clock tower, as well as a chain drive. Su Song's clock tower, over 30 feet, 9.1 m, tall, possessed a bronze power-driven armillary sphere for observations, an automatically rotating celestial globe, and 5 front panels with doors that permitted the viewing of changing mannequins which rang bells or gongs, and held tablets indicating the hour, or other special times of the day. Today, in Beijing's Drum Tower, an outflow clepsydra is operational and displayed for tourists. It is connected to automata so that every quarter hour a small brass statue of a man claps his cymbals. Greco-Roman world. An early 19th century illustration of Alcestis' clepsydra, from the 3rd century BCE. The hour indicator ascends as water flows, and also, a series of gears rotate a cylinder to correspond to the temporal hours. In Greece, a water clock was known as a clepsydra, water thief. The Greeks considerably advanced the water clock by tackling the problem of the diminishing flow. They introduced several types of the inflow clepsydra, one of which included the earliest feedback control system. Alcestis invented an indicator system typical for later clocks such as the dial and pointer. The Roman engineer Vitruvius described early alarm clocks, working with gongs or trumpets. A commonly used water clock was the simple outflow clepsydra. This smaller thinware vessel had a hole in its side near the base. In both Greek and Roman times, this type of clepsydra was used in courts for allocating periods of time to speakers. In important cases, when a person's life was at stake, for example, it was filled. But, for more minor cases, it was only partially filled. If proceedings were interrupted for any reason, such as to examine documents, the hole in the clepsydra was stopped with wax, until the speaker was able to resume his pleading. In the 4th century BCE, the clepsydra is known to have been used as a stopwatch for imposing a time limit on clients' visits in Athenian brothels. Slightly later, in the early 3rd century BCE, the Hellenistic physician Herophilos employed a portable clepsydra on his house visits in Alexandria for measuring his patients' pulse beats. By comparing the rate by age group with empirically obtained data sets, he was able to determine the intensity of the disorder. Between 270 BCE and 500 CE, Hellenistic Alcestis, hero of Alexandria, Archimedes, and Roman horologists and astronomers were developing more elaborate mechanized water clocks. The added complexity was aimed at regulating the flow and at providing fancier displays of the passage of time. For example, some water clocks rang bells and gongs, while others opened doors and windows to show figurines of people or moved pointers and dials. Some even displayed astrological models of the universe. The 3rd century BCE engineer Philo of Byzantium referred in his works to water clocks already fitted with an escapement mechanism, the earliest known of its kind. The biggest achievement of the invention of clepsydra during this time, however, was by Alcestis, with his incorporation of gears and a dial indicator to automatically show the time, as the lengths of the days changed throughout the year, because of the temporal timekeeping used during his day. Also, a Greek astronomer, Andronicius of Cyrrhus, supervised the construction of his horologion, known today as the Tower of the Winds, in the Athens marketplace, or agora, in the first half of the 1st century BCE. The octagonal clock tower showed scholars and shoppers both sundials and mechanical hour indicators. It featured a 24-hour mechanized clepsydra and indicators for the 8 winds from which the tower got its name, and it displayed the seasons of the year and astrological dates and periods. Medieval Islamic world. Al-Jazeera's elephant water clock, 1206. In the medieval Islamic world, 632-1280, the use of water clocks has its roots from Archimedes, during the rise of Alexandria in Egypt, and continues on through Byzantium. The water clocks by Persian engineer Al-Jazeera, however, are credited for going well beyond anything that had preceded them. In Al-Jazeera's 1206 treatise, he describes one of his water clocks, the elephant clock. The clock recorded the passage of temporal hours, which meant that the rate of flow had to be changed daily to match the uneven length of days throughout the year. To accomplish this, the clock had 2 tanks. The top tank was connected to the time indicating mechanisms, and the bottom was connected to the flow control regulator. Basically, at daybreak the tap was opened and water flowed from the top tank to the bottom tank, via a float regulator that maintained a constant pressure in the receiving tank. Water-powered automatic castle clock of Al-Jazeera, 12th century. The most sophisticated water-powered astronomical clock was Al-Jazeera's castle clock, considered by some to be an early example of a programmable analog computer, in 1206. It was a complex device that was about 11 feet, 3.4 m, high, and had multiple functions alongside timekeeping. It included a display of the zodiac, and the solar and lunar orbits, and a pointer in the shape of the crescent moon which traveled across the top of a gateway, moved by a hidden cart, and causing automatic doors to open, each revealing a mannequin, every hour. It was possible to reprogram the length of day and night in order to account for the changing lengths of day and night throughout the year, and it also featured 5 musician automata who automatically play music when moved by levers operated by a hidden camshaft attached to a water wheel. Other components of the castle clock included a main reservoir with a float chamber and flow regulator, plate and valve trough, 2 pulleys, crescent disc displaying the zodiac, and 2 falcon automata dropping balls into vases. The first water clocks to employ complex segmental and epicyclic gearing was invented earlier by the Arab engineer Ibn Khalaf al-Muradi in Islamic Iberia. 1000. His water clocks were driven by water wheels, as was also the case for several Chinese water clocks, in the 11th century. Comparable water clocks were built in Damascus and Fez. The latter, Dar al-Magana, remains until today, and its mechanism has been reconstructed. The first European clock to employ these complex gears was the astronomical clock created by Giovanni da Dondi in c. 1365. Like the Chinese, Arab engineers at the time also developed an escapement mechanism which they employed in some of their water clocks. The escapement mechanism was in the form of a constant head system, while heavy floats were used as weights. Korea. In 1434, during the Chosun, or Joseon, dynasty, Chang Yongsil, or Jang Yongsil, palace guard, and later chief court engineer, constructed the Jjiengnu, self-striking water clock, or striking clepsydra, forking sejong. What made the Jjiengnu self-striking, or automatic, was the use of jackwork mechanisms, by which 3 wooden figures, jacks, struck objects to signal the time. This innovation no longer required the reliance of human workers, known as roostermen, to constantly replenish it. By 1554, the water clock spread from Korea to Japan. Water clocks were used and improved upon throughout Asia well into the 15th century. Modern water clock designs. Only a few modern water clocks exist today. In 1979, French scientist Bernard Guérin began creating his time flow clocks, which are a modern-day approach to the historical version. His unique glass tube designs can be found in over 30 locations throughout the world, including one at Europa Centers, the Clock of Flowing Time in Berlin, Centre Commercial Milanese in Guadeloupe, the giant water clock at the Children's Museum of Indianapolis in Indianapolis, Indiana, and the shopping Iguatemi in Sao Paulo and Porto Alegre, Brazil. Guérin's design relies on gravity powering multiple siphons, and same principle as the Pythagorean cup. For example, after the water level in the minute or hour display tubes is reached, an overflow tube starts to act as a siphon, and thus empties the display tube. Actual timekeeping is done by a calibrated pendulum powered by a water stream piped from the clock's reservoir. The pendulum has a carefully constructed container attached to it. This measures the water that is then poured into the display system. There are other modern designs of water clocks, including the Royal Gorge Water Clock in Colorado, the Woodgrove Mall in Nanaimo, British Columbia, in the Abbotsford Airport in Abbotsford, British Columbia, and the Hornsby Water Clock in Sydney, Australia. Temperature, water viscosity, and clock accuracy. The rate at which a fluid passes through an orifice depends, other things being equal, on the viscosity of the fluid. Approximately, the flow rate is inversely proportional to the viscosity. The viscosity depends on the temperature. Liquids generally become less viscous as the temperature increases. The reverse is true of gases. In the case of water, the viscosity varies by a factor of about 7 between 0 and 100 degrees Celsius. Thus, a water clock would run about 7 times faster at 100 C than at 0 C. Water is about 25% more viscous at 20 C than at 30 C, and a variation in temperature of 1 degree Celsius in this room temperature range produces a change of viscosity of about 2%. Therefore, the water clock that keeps good time at some given temperature would gain or lose about half an hour per day if it were 1 degree Celsius warmer or cooler. To make a keep time within 1 minute per day would require its temperature to be controlled within 130 C, about 117 Fahrenheit. There is no evidence that this was done in antiquity, so ancient water clocks, unlike the modern pendulum-controlled one described above, cannot have been reliably accurate by modern standards.